As an application of our conditions of equilibrium, I'd like to look at a special case, which is known as the case of concurrent forces. If you have a body that's subjected to a set of forces, and the lines of action of all the forces pass through a common point, then we call those concurrent forces. So in this case over here, I have force F1, F2, and F3, and the lines of action of the three forces all pass through this point right here, which I've labeled O. Okay, and when you have this situation here, if you calculate the resultant moment, you'll find that the resultant moment is 0. And the resultant force, of course, is simply the sum of those forces that are acting on the body. The thing that makes this situation nice is you don't have to consider the case of the moments. You only have to check that the net resultant is equal to 0 for equilibrium, because you know a priori, because of the concurrency, that the net moment is equal to 0. So this can simplify a lot of problems. So let's look at a simple problem that falls into this category. So here I have a box, and the box has some kind of weight to it, say 100 newtons, that's acting downward, and it's supported by two ropes. So I have rope 1 over here, and I have rope 2. Rope 1 is at 45 degrees because the rise and run are both the same, 4 meters here. And the ropes pass over some pulleys in each case, and these pulleys are what we call ideal pulleys. Ideal pulleys are frictionless, and when you have ideal pulleys, you have the situation that the forces in the ropes actually turns out to be constant everywhere along the rope. So if I pull on this end over here with 100 newtons, that means I'm pulling actually over on this end also with 100 newtons. And we'll prove a little bit later that this in fact is true, but right now let's just assume that as a fact. And in this problem, what I'd like to do is find what the angle alpha and the force F is in the second rope for the system to be in equilibrium. So to start such problems, we always start with a free body diagram. So let me redraw the box, and I'll go ahead and include the I at the top. We have the 100 Newton weight coming straight down. Off at 45 degrees, I also have 100 newtons, so I've isolated the I from the rope and just included the force of the rope. And I also have this force F over here, and F is at this unknown angle alpha that I need to find. So let's go ahead and draw this again. So let me just draw the point E. We have a force of 100 newtons. This 100 newton force in a vector sense is at 45 degrees. So this is at 1 over root 2 EX plus 1 over root 2 EY. So that's the unit vector at 45 degrees. We have our other force over here, F, and this one is acting at minus cosine alpha EX plus sine alpha EY. And then we have the downward force, which is 100 EY. And so that's, we can write that as minus 100 EY. And throughout, I've made this tacit assumption that my coordinates are oriented x and y, x horizontal, y vertical. So we sort of have two choices here about completing the solution for the unknowns alpha and f. And one way is to note the fact that if you add vectors, you can kind of lay them out head to tail, and if they're going to add up to 0, you have to have a closed polygon. So let me go ahead and do that version first. So if I put an arrow length 100 going straight down, another arrow of length 100 where this angle here is 45, so pi over 4 in radians, and then the closure of that triangle is with a line or vector of length f. And I know that the angle that f makes with the horizon is is alpha. So that means that this angle here is pi over 2 minus alpha. And since the sum of the angles has to be 180 degrees, this tells me that this angle in here is pi over 4 plus alpha. So from this diagram, I could use, say, the law of sines to determine my unknowns. So f is divided by the sine of pi over 4 has to equal 100 over the sine of pi pi over 2 minus alpha, and that's also equal to 100 divided by the sine of pi over 4 plus alpha. So this is the law of sines, just drawn for this triangle over here. So if I use the second equality over here, the second equality tells me that alpha has to equal pi over 8. And once I know what alpha is, I could use, say, the first equality over here, and that's going to tell me that f is equal to the sine of pi over 4 times 100 divided by the sine of pi over 2 minus alpha, which is going to be equal to 76.5 newtons. So that's one way of doing this. So law of sines or law of cosines is often useful when you only have 3 forces in the problem. The other way to do this is just go component by component. So if I sum the forces in the horizontal direction, I have minus f cosine alpha plus 100 over the square root of 2 equals 0. And if I sum the forces in the vertical direction, I have f sine alpha plus 100 over root 2 minus 100 equals 0. So I have 2 equations, and there's 2 unknowns. So if I take the constant terms here to the right-hand side and divide one equation by the other, I can show that the tangent of alpha is equal to the square root of 2 minus 1, which tells me that alpha is equal to pi over 8. So that's the same result that I had before, and I can then plug back in, and then I'll find again that f is equal to 76.5 newtons. So there's sort of 2 ways of doing this. One is if you can draw something geometric and then try and use things like law of sines and law of cosines, or you can go component by component, write out the linear equations that you have for each direction, and then try and solve those equations.